I'm audible, right?
Yes, sir.
Well, as well.
Yes, sir.
Yeah. All right. Let's start. I guess it's already been delayed by 15 minutes. What is the question, Karan? Will the answers of questions not uploaded? What questions? You mean the coding questions? I have given you the credentials of the Lead Code account, right? You can log in and check out the answers. Right? Does that answer your question, or is are you asking something else, Karan? What do you mean the answers are not visible? Like it's the same credentials that I used to log in. You can check my previous submissions, right? And you can see the answers. Yeah, it's the same. I have used the same login to submit my solutions. Yeah. Okay. Let me know if you are still facing issues. We will be happy to resolve. All right. Let's start then. And yesterday we were talking about time complexity in particular, and I told you that so we were talking about time complexity. Today's agenda, I will just tell you. Today we will wrap up our discussion on time complexity, and then we will, after that, we will wrap it up, and then we will start with binary search, and we will look at the predicate framework of binary search and how we can use that to solve questions, binary search questions with ease. So we will, that's basically the agenda for today. And so first of all, does anyone have any questions with respect to yesterday's lecture? Anything you don't understand from yesterday's class? Nothing, right? All good? Okay. All right. Then yesterday we were discussing about time complexity, and we were, in particular, we said we were, I'll just summarize our discussion of time complexity that we did till then. So we said that we want to measure, we write programs, right? We write programs for computers to consume and execute. We want to measure the time that programs take to run on a computer. Programs take to run. And we want an approximate analysis of this so that we are able to compare two programs which do the same task. We want to compare which program is faster, which program is slower. So that's basically the objective of doing this time complexity analysis. And then we said that okay, but this analysis will always be dependent on the size of the input. So this size, this input cannot be, is always a factor in that you need to take into account when you are doing the time complexity analysis, because the same program will take different time for different inputs. Okay. The other factor that we need to keep in mind when we are doing this time complexity analysis is that we want the analysis to be independent of the underlying hardware. So we just want, so the same program basically, depending on the hardware configuration, depending on the CPU clock cycle, depending on the amount of RAM, the gigs of RAM that is available, might run with different speeds on different computers. So we don't want to that, we want to keep that variable also constant when we do a time complexity analysis. So these are some factors into consideration when we are doing some factors to be considered when we are analyzing complexity of programs that we as programmers write. So then I just gave you some notations that we can use to measure the complexity of programs. And I said that we are always interested in an upper bound on the time that a program takes to run on a computer. We want that time to be upper bounded by a quantity, and typically we use big O notation to represent that kind of an upper bound. On the other hand, we can also have lower bounds on the running time of the program, wherein we say that the program will take at least this much time to run. And so typically we will use omega to denote such kinds of time complexities. And then we said that we are also interested in the exact tight bounds, which is basically roughly what the exact time that the program takes to run, and that typically can be denoted by theta. So that's all we have done so far. And I just gave you some examples that if I say that a program is order of n, this basically means that the program's running time grows linearly with the input size. So what does that mean? That means that if you have an input, let's say x, and the program takes some time t, then for input x square, the program will take time t square, right? It's linear. The relationship is linear, roughly, right? This is how we denote it. And this running time, this is the upper bound. Similarly, if we say that if a program's running time is order n square, then we are saying that as the input grows, the program becomes quadratic. The program's running time becomes quadratic. The upper bound on the program's running time becomes quadratic. So if it were taking 3 seconds on some input x, and let's say now you have changed the input to, let's say, 2x, not really 2x. If it were taking 3 seconds on input x, then on input x square, how much time will it take? If I say this roughly, 9. Will it be 9? Yeah, it will be 81. Right? I said that on input x, it takes 3 seconds. So when you have squared the input, the time that the program takes will become power 4. Do you follow this? Because this is order n square. So that basically means that the running time is quadratic with respect to the size of the input. Do you want me to prove it mathematically, or intuitively it makes sense to everyone? So now you have some feeling about the time complexities, right, everyone? So this is, I mean, for our practical purposes, we are good enough with this much knowledge. We don't really need to go into the mathematical details of what a big O means, what omega means, what theta means. We can, for all our practical purposes, I guess we are good with this much amount of information. Okay. So then I told you that I gave you an example. Let's say this is a for loop that I told you. Let's say I told you that, let's say this is a program where n is the input, and this program is printing this. So what is the complexity of this program, assuming this this entire statement takes 1 unit of time? This is order n, right? This is n, right? This is both order n as well as theta n also, and omega n also, you can say. Okay. So then I told you that what if I write the same program, and now I have two couts. Let's say I'm printing I here, and let's say I'm just printing hello. So what is the complexity of this? This is still 2n. Right? This is 2n. But yeah, and so I told you to tell me why is this still order n?
Because loop runs only n times.
Okay, so what? Yeah, the loop might run n times, but it is a constant factor of n. So what does that mean? If we double input size, time to run is doubled. And is last, so constant multiplied can be ignored. So, I mean, this obviously takes twice the time that this program took to run, right? There is no doubt about that, because you are doing 2n operations here, you were doing n operations here. So this will definitely take twice the time. That is okay. But in terms of order notation, if I have to find an upper bound for this program is still upper bounded by n. That's because, so there is a difference. I told you that the program no doubt takes 2n times. There is no doubt about that. But if I have to denote this in order notation, this will still be order n. And that is because when we do an analysis of order, or when we use these notations, we assume that the input is very large. So we are primarily interested in how the program behaves for large inputs. Does it behave linearly? Does it behave quadratically? Does it behave exponentially? How the program behaves for large inputs. That's what we are interested in. Why is it? Because obviously the bottleneck when you are talking about time will come for large inputs, right? So the bottlenecks will obviously be for large n. And that's why whenever we do analysis of complexities of programs, we say that, okay, this program I have written. Now tell me, if I give this program a very large input n, what is the complexity of this program? How much time will it take with respect to this n? And then you say, okay, this program takes order n. What does that mean? That means that if you run this program for this large input, this program's running time behaves linearly, grows linearly with n. So for large n's, if you take two very large n's, n1 and n2, such that n2 is n1 square, and your program is taking order n, then basically, if your program is taking x time for n1, then for n2 it is taking x square time. That's what you mean when you say that the program is order n, right? Do you get this? Do people get what I'm trying to say here? Does it make sense why we consider large inputs? Because that's the bottleneck. Whenever we are running programs, if inputs are typically small, I mean, most programs will work fine, will give us an output within the required time limits. But the real problem starts arising when the input starts becoming very large. And that's when we want to know how the program is behaving, or uh, how fast the program is running. That's why we say that give me the behavior of the program for large inputs, for big inputs. And that's why we say that, okay, if you want input for big inputs, the program is behaving as order n. So that basically means that if you double the input size, then the time will also double. But these are all for large n. So that's why now when you change the program to for the same input size, let's say now you change the program to add one more line extra, then it is taking 2n time, no doubt about that. But the behavior with respect to n is still linear, right? Because 2 is very small compared to n. Do you get this? What I told here? Yeah. So that's why even if we in the for loop we say, but if in the for loop, let's say now we do cout n by 2 times, then what happens? Then is this program still order n? Do you get the question?
So could you repeat the question?
The question is, let's say in the for loop that I was taking example, now I am doing, previously I was doing cout 2 times. Now I am doing cout n by 2 times. So now I want you to tell me that previous program was a for loop with one cout. And this, we said that runs in order n. What does that mean? That means that it grows linearly with the size of the input for large inputs. That's what we mean in English for this program. So now I am asking, what is the complexity of this program? Yeah, the complexity for this program will become n square now. Because now you are doing it n by 2 times. So what does that mean? That means, so the total time is n by 2 into n. Previously it was 2 into n. Okay. So now just think about the case when n is very large. When n is very large, 2 into n is, like, for all practical purposes, it's nearly the same as n. So you can still say that it is upper bounded by n. Okay. But if n is very large and you are doing n by 2 into n, you cannot say that it is upper bounded by n. N by 2 into n is not nearly the same as n for large n, right? It is n square. So now this program has started behaving quadratically with respect to input. So with input size, as the input size grows, this program is growing quadratically. Cout is just printf, printf. You're printing something on the screen. Just one instruction. Let's say n++, you can say anything. Cout is to print and print to the console. So when you do cout x, then you print the value of x on the to the output. I mean to the console. Okay. Yeah, it's just. I mean, yes, it's C++'s way of outputting to that console. You can read about the syntax of it, but you will see us using that also. So you will get acquainted to it also. Okay. Others, do you understand why this is not n now? And this is n square? So all the analysis is with respect to large n's. That's what we want to do. Okay. So that basically, I mean, roughly brings us to the end of time complexity. So I'll just summarize what we discussed in this. We said that we want to analyze the running times of programs, running time as in the time that the program takes to run for large inputs. We want to analyze running time of programs, and we know that this running time R will be proportional to the size of the input, and we want to analyze it for large n's, because small n's, it's trivial, we don't want to. And so we said that, okay, and we want to analyze it independent of the underlying hardware, independent of hardware. And we said that, okay, there are certain notations you can use to denote the running time of the program, which are big O, omega, and theta. Big O basically means that the program is upper bounded by whatever is in the bracket. So that basically means that the program. So if you say big O of n, it basically means that the program for large n, the upper bound of the program grows linearly. For omega n, omega n square, let's say, it means that for large n, the lower bound of the program grows quadratically. Let's say the theta was e to the power n, then it means that for large n, the tight bound of the program grows exponentially with n. So as you, can you tell what is, there is no there is no hardcore number, sorry. It is basically asymptotic. So these are called asymptotic notations, which basically means what are asymptotes? Asymptotes are, do you know what are asymptotes in graph? What? Tell me, can you unmute? Asymptotes are lines which meet curves at infinity, right? Yeah. So these are asymptotic notations. So very large n, I mean, typical, I mean, theoretically it's close to infinity, like very large n, how the program behaves. Come again, can you unmute and speak, Aman?
Sir, are these three relations always true? Like the relation of big O with n, omega with n square, and so on?
This is, I just gave examples. Big O is a function. So it's like a notation. So you say, it's almost like saying, see, you can simply say that my running time is n. You can say my running time is n. That's okay. The other way of saying it is that my running time is big O of n. What that means is that my running time is upper bounded by n. Or mathematically, it is basically less than equals to C of n for large n. That's what it means. So basically what it means is that my current program, if I take an input of size n, my running time is upper bounded by n. Okay, so big O is just a notation. Big O of n, it can be big O of n square, big O, C is a constant. Big O of n cube, it can be anything. Big O of e to the power n. That's not the point. Point is that it's just a notation to say that the upper bound is n. What that means is that by a constant, the running time is always upper bounded by some constant multiplied by n. This is just one way of saying. Similarly, if you say omega n, you are saying that my running time is greater or equal some constant times n. If you say my running time is omega n square, then you say that my running time is greater or equals some constant times n square for large n's. For large n's, I can always find a lower bound for my running time, which is greater than this expression. For large n's, I can always find a upper bound for my program, which is less than this expression, less than or equal to this expression. Right? Up to some constant we allow. We cannot just exactly say, we don't want to just say exactly that the running time is 2.22 and just order notation, just in terms of the input, how it varies. Right? Any more questions? No more questions? Shall we move on? Okay, now I need your full attention because today we will start binary search, and half an hour from now things will be flying over your heads. So please try to follow. We will do binary search today. So let's start with searching. What is searching? Login complexity. What is searching? Can anyone tell me?
Just searching an element in a sequence, like in an array. Find a particular element.
Okay. I will formalize that more. So searching is basically you are looking for an item. And when I say an item, this item has certain properties. So what you are doing when you are searching is that you are looking for an item which has certain properties in a search space. So the search space is basically the entire space where all the items are present. And you have to, can you unmute? Can you mute yourself? Yeah, thank you. So search space is the space where all the items exist. So a typical example that I give generally when I explain searching is a supermarket. Let's say you have been told by your mom or your girlfriend or your sister or your brother to go to a supermarket and get a carton of milk. So you know that milk, in your mind, you know that milk has certain properties, right? You know that milk has a color which is white, milk is liquid. You know that milk has a certain density or viscosity. Then you know that milk will come in a Tetra Pak that I'm looking for, and it will be of blue color, the Tetra Pak. You know certain properties of the item that you are looking for. And then you enter the supermarket. So your supermarket is the search space, the space where you have to search for the item. So the supermarket contains all the items, all possible items, milk, toys, let's say vegetables, fruits, groceries, everything. And you have to find milk there. So that's what I mean when I say that item and a search space. Search space is the space where you have to search, and an item is something that you are looking for, which has some properties which you have in your mind. Now, what is one typical algorithm that you could employ to search in the supermarket? You could start from enter the supermarket. You could pick up item I1, the first item. You could look at it, see its properties, and see if they match the properties that you already have in your mind for milk. If they don't match, you can keep it down. You can conclude that, okay, this is not milk. Let's move on. Let's move on to second item. So then you can go to the next item, and you can tell yourself, you can again tell yourself, okay, is it milk? Let's say it's not milk, then you will again put it back in the place, and then you will move on. This way you can just keep inspecting every item in the supermarket one by one. And finally, let's say you get an item IK whose properties match the properties of milk that you have in your mind. And then you conclude, yes, this is what I'm looking for. So then you basically go to the billing counter, get it billed, and then you come out and your mom is happy, right? So this is one typical searching algorithm which you could use, which is the brute force way of searching, which is basically inspecting every element and find until you find the desired element. Okay, this is one way of searching. No rocket science till now. I have just told you what you already know. Now let's make it a little more complicated. Now suppose that this supermarket, the owner of the supermarket, he's a nice man. He understands your problem. He understands that typically you take a lot of time when you are looking for milk, because you have to physically examine each and every item one by one before you can find the milk. So the owner has one idea. The owner tells his store workers that organize all the items in racks and label each rack. So organize items in racks R1, R2, R3, R4, and label each racks. Label R1 as, let's say it's only produce items in R1. Let's say you have only groceries in R2. You have only refrigerated items in R3. You have healthcare or lifestyle items in R4. So the store workers go ahead and implement this. So they now have racks, and each rack is very clearly labeled as to what category of items are present in that rack. So now on one fine day, again your mom tells you, go get me a milk carton. So now you again enter the supermarket, and this time you are smart. So you have an idea. You conclude that my milk is definitely not a produce. So I don't really need to check R1. It is also not in the groceries, so I don't even need to check R2. So in that way, you come to R1, you read this title, and you conclude that, okay, I don't need to really examine elements of R1 because I know that milk is definitely not one of them. So I can safely skip all these elements and move on to the next track. So now you come to R2, you again do a similar analysis, and then now you come to R3. And now you see, okay, R3 contains refrigerated items. So my milk is also one refrigerated item. So this is the place where I will get my milk. And then you walk down the aisle and you inspect every element manually and do a process similar to what you were doing before, checking the properties, and once found, you can return. So what has this achieved? This has saved you a lot of time. So you were able to optimize your search, because now hear this out very carefully. you were able to optimize your search because the search space had certain properties which enabled you to search efficiently, right? What was the property of the search space in this example which enabled you to search efficiently? Separate routes, right? Categorization. Yeah. So this property of the search space allowed you to skip certain sections of the supermarket because and intelligently search in a efficient manner. And now you are happy, your mom is happy, you return from the supermarket half an hour before you were supposed to, or you generally do. Okay, so to summarize what I have told you till now is I just defined searching for you. I told you that searching is nothing but looking for an item with certain properties in a search space. And I told you that searching, there are a wide variety of algorithms which you can use for searching other than the brute force way of doing it. All these algorithms, the efficiency of these algorithms depends on the search space. So certain, if a search space satisfies certain properties, then it might enable you to search efficiently. So binary search is one such algorithm which operates on, so binary search is one such algorithm which is not applicable on all search spaces. So let's say this is the universe of all kinds of search spaces. Binary search is only applicable on certain types of search spaces. These search spaces have certain properties which they need to follow so that you can intelligently do binary search and search in an efficient manner, right? So this is the point that I'm just trying to drive home, that the efficiency of a searching algorithm depends on the property of the search space. If the search space has certain properties which enables you to search faster, then you are good. Okay. So far, this is all I have told you. So now let's get into binary search. So our discussion of binary search will we will first look at what properties a search space needs to have in order for binary search to be applicable. This is the first thing that we will look at. And once we know that, okay, so any problem that you get, any searching problem you get, you will first look at the search space and you will check whether the search space has this property or not. If the search space has this property, then you will say, okay, now binary search is applicable. I can apply binary search on this. So then once you have determined that binary search is applicable, you will then, I will tell you that using binary search, what elements of the search space can you find in log n time? Okay, so I just told you two things. I told you now we are about to discuss binary search, and we will first look at all the properties that a search space needs to have so that you will be able to apply binary search on it. That's one thing. Once you have determined that you can apply binary search on it, there are only certain elements of that search space which you can search for in log n time, even in that search space. And that is what we will discuss then, that what kinds of elements can you search for in that search space once you know that that search space has those properties which enables you to apply binary search, right? And then I will give you the code to search for these elements. Search for elements described in 2. That's it. So typically, this is our very high level how we will approach this binary search topic. Now, after this, basically, if you get any question, what you need to do is you need to first check whether in the question, the search space that is given in the question, does it have the properties so that I can apply binary search? Once you determine that, okay, it has the properties and I can apply binary search, will that application lead me to the answer that the question is looking for? Why? Because even with that, even if binary search is applicable, I know that I can only find certain elements of the search space, not every element. So those certain elements of the search space, which I will tell you in this too, will finding those elements help me in solving the actual problem that I have at hand? That I will do next. If it is, then I will simply use the code to search for that element and then use that element's result to solve the actual problem. This is the typical approach that I will be using for a binary search question. ये दोनों चीजें समझ आई क्या? I just told you 2 things: how we will approach the binary search topic, what all we will, how we will study it, and then I told you that if once we have this theory in our artillery, we will be approaching questions in this order, in this manner. This is the
point 2 on the right hand side.
Point 2 on the right hand side. You want me to repeat? So I told you that once you have a problem at hand, okay, you have some lead code question that they want you to solve. You see a search space in that question. You check the properties of that search space and you determine that, okay, binary search is applicable on the search space. That's what you have done. Now, then after that, even now you know that binary search is applicable on the search space. You know that even then, out of all the elements of the search space, there are only certain elements you can search in log n time. You cannot search for any element. So you will then determine in step number 2, will finding these elements or one of these elements help me in solving this actual problem that I have at hand? If yes, then I will use the code to find one of these elements, whichever element will help me in solving the actual problem. And then once I have found this element, I will use that result to solve the actual problem. Do you get it?
How exactly did order of log n come into picture?
I mean, for now, you can just say efficiently. That should be fine. But typically, binary search is basically it enables you to search in log n is basically the size of the search space. Did I answer your question, Suraj?
Yes, sir.
Sharad, what is the question? Why only one of them? No, I'm not saying one of them. I'm just saying that this is a very high level approach that I'm telling you. So you might need to find more than one. Out of all the elements which you can find using binary search, you will need to find some of them or all of them or one of them. You don't know, but you will have to make an estimate then that will my finding those elements help me in solving the actual problem that I have at hand, right? It might not be a straightforward search problem, right? It might be some other type of problem for which you need to find this and then use that index to do something, let's say. So I'm just telling you a more a more general idea. Right? Did I answer your question? हाँ, और किसी को कोई डाउट अभी तक? Make sure you understand things abhi gaps will start accumulating. Everyone is fine? Can I have Axe quickly?
Yes, sir.
Yeah.
Sir, what if the elements, like if the element which we choose, like if an element in the search space that solves the problem cannot be searched in the login time.
Yeah, then this does not come, and this is not the scope. I mean, binary search is not really the way to go forward with it, right? We are just discussing questions for which this can be applied, and if this can be applied, how we will be applying it. If that finding that element does not help you solve the original problem, then there is no point in doing this exercise. It might be a problem of involving some other algorithm or some other technique, right? Okay. So now listen carefully. Now we'll have some maths and some. So now we will answer the first question, which is when to apply binary search. So what is the property of the search space which enables us to apply binary search? So now listen very carefully. So now there is a theory that, first of all, let's define certain terms. We will define a predicate. So predicate is nothing but a binary function or a Boolean function with integer as an input and a I mean with anything. It can be anything, integer, reals, or numbers or strings with Boolean value as an output. That's the only thing. So predicate is a function which takes, it can take anything as an input. It can take an integer, a real number, a string, a word, a sentence, anything, and it will give you either true or false. Okay. So this is predicate. This is just some terminologies that we are defining for ourselves, which will make our lives easier once we are deep into the theory of binary search. Then after predicates, you have search spaces. I guess you know that. So then you have applying predicates on a search space. So when I say applying predicates on a search space, I basically mean that I have my search space. I have elements in that search space. I am, let's say, E1, E2, E3, E4, E5, E6, E7, and so on. So when I'm applying the predicate on that search space, I am defining a function which basically maps every such element. I'm defining a predicate which maps every such element of the search space to either true or false. So P1 can be true or false. P2 will be either true or false. P3 will be something true or false. Okay, and so on till P9. All the elements of the search space, I have defined a predicate over all the elements of my search space. Okay, these are some terminologies that we need to keep in mind. Clear with predicates? Nobody has any questions on predicate, right? It's just a Boolean function, which is Boolean as the range, right? This, make sure you remember predicates and applying predicates, because now I will write some things. So now we will tell when is binary search applicable. This is the question that we are trying to answer. Now the theory says that binary search is applicable if you can find a predicate on the search space such that for A and B belonging to the search space, P of A implies P of B for all A less than B. We will decrypt it, don't worry. But this is basically the theory. So what we are saying is that binary search can be applied on a particular search space if you can find a predicate such that you apply that predicate on the search space. What does that mean? That means that you define a Boolean function over all the elements of the search space. And once you have defined that Boolean function, what you do is you put out all the items of the search space in some order. Let's say this order, such that A1 is less than A2, less than A3, A4, A5, A6. And you apply predicates on each of them. PA1, PA2, PA3, PA4, and so on till PA6. So then if after applying predicate on this, you get a pattern which is a series of falses followed by a series of trues, then binary search is applicable. So what this means is, this is series of falses followed by a series of trues is what is written in this line. That if the predicate evaluates to true for A, for some A which is less than B, then the predicate evaluates to true for all the B's which are to the right of A, which are greater than A, which is what is encapsulated by this. Okay. And what is the contrapositive of this? It is not PB implies not PA for all A less than B. What does that mean? That means that if you have false for one particular element of the search space, then for all the elements to the left of it, you will also have false. Correct? So I'm not expecting you to have an intuition for this right now. You will get an intuition once we start solving problems. But right now, I just want you to understand the what of this theorem. Just the what it says. That's it. Are you able to understand that? Which part do you want me to repeat, Tanya? Yeah, so I'm just saying, just read this line. What is this line? PA implies PB. What does that mean? That means that if PA is true, then PB is also true for all B greater than A. That's what we have written here, right? So what does that mean? That means that if for some item of the search space, you evaluate the predicate and it comes out to be true, then for every item which is greater than this item, the predicate should evaluate to true, right? This is what it means with this line. And now read the contrapositive of it. Do you understand what contrapositive is? A implies B is contrapositive is not B implies not A. So both of them are equivalent. Okay. So now see the contrapositive of it. Contrapositive of it is not PB implies not PA. What does that mean? That means that if for one item of the search space, your predicate evaluates to false, then for all items which are less than this item, the predicate should also evaluate to false. That's what is meant by this line, right? So what is the resulting pattern or the sequence that emerges? It is series of F's followed by a series of T's, which is in regular expression, you can write F star T star, right? 0 or more F's followed by 0 or more T's. So basically, we are saying that you apply a predicate on a search space, and if you are able to reduce the search space to an F star T star pattern, then binary search is applicable on that search space. Or the equivalent definition is you can apply and reduce it to a T star F star pattern. Both of them are equivalent, but we will not focus into T star F star. We'll keep this. one by one. Akshat, what is the question? How to compare items?
So like, how do we know that even like the items need not be numerical?
Yeah, I don't care. I mean, there will be some ordering defined by that. There will be a less than operator which will make sense for the items, right? It can be anything. If it is strings, it might be lexicographic comparison. That's you can abstract that out. You don't really need to bother about that. You just say that I have items in my search space and there is an ordering in the search space. Obviously, there will be less than will make sense.
So we need not bother about that. We just need to check whether it is applicable or not.
Yeah, I mean, whatever search space you will be given, the less than operator will make sense in that search space. What is the question exactly, Akshat?
So like, I was thinking that all the elements need not be numerical, so that less than makes sense for every kind of items. Like a search might contain string.
You are talking about a search space which has heterogeneous items. Let's say some
Yeah.
strings, I don't care, but that's not my concern. There will be an ordering which will be defined for you. So there will be some notion to say that 9 is less than Akshat, let's say the string Akshat. That will be there. That search space, any search space you will encounter will have an ordering defined. Right? It will be comparable. You should be able to compare items of that search space.
Okay.
Just that much. You can abstract it to that level. You don't really need to go into what exactly is the composition of the search space. But for us, it is basically the search space is comparable. You can compare the items of the search space. I don't care if it is a heterogeneous search space or a homogeneous search space. It has numbers, decimals, strings. I don't care. But there is you can compare them. Right? Did I make sense?
Yeah. Yes.
I mean, you can ask follow up if you are not convinced. There is no harm.
Clear.
Yeah, Mrigank, we will take an example right now, but okay, let's take an example and then I will take more questions. Let's say you are given this array 2, 3. You're given an array 2, 3, 5, 7, 10, let's say. And you are given a target which is 9, some t. I define a predicate on this array px, where x is less than t. You have to tell me, can I apply binary search on this search space with this predicate? So just you have this as your search space 2, 3, 5, 7, 10. Apply the predicate. So what is P of 2? P of 2 is 2 less than 7, 2 less than 9. Is it false? It is true. Okay. Is 3 less than 9? True. Is 5 less than 9? True. 7 less than 9? True. 10 less than 9? False. So what is the search space? It is a series of T's followed by series of F's. So you can say that binary search is applicable on this. Right? Does everyone get some idea? Sai Sriram, do you understand?
So what if we have a series of false only and we don't have any trues?
That is also fine. That's why I wrote F star T star. So star, I did not write plus. This is a regex, right? So 0 or more Fs followed by 0 or more Ts. So I can have a sequence entirely of Fs or a sequence entirely of Ts. Both of them, it is applicable. I did not write F plus T plus, right? Which basically meant that one or more Fs. This regular expression you are familiar with, right? I'm assuming. Just the basic, the wildcard, at least the wildcard character, not too much. Yeah, Kush, did I answer your question? No, Akash, predicate will not be given to you. That's the beauty. You have to find a predicate such that binary search is applicable on that search space with that predicate, and then use that predicate. That's the whole crux of solving problems, finding predicates. We will practice them. So let's take another example. I have a sorted array. Now this is what you have been doing all your life. You have always been given a sorted array. Yeah, I'll give you an example, don't worry. I have a sorted array and I have a target which I want to find. My question is, can you give me a predicate such that binary search will be applicable on this search space with this predicate? So you have done this all your life, right? Sorted array, you know that I can find a key with binary search. That's the level that we know as students, the level of binary search that we are taught. So now I am just telling you to prove this formally, that binary search, you can apply binary search on this. Just give me a predicate. Do you understand the question, everyone? Just think a little bit with respect to the target.
So what exactly is target again?
Target is a number that you need to find in the array. So you are given an array, a sorted array, and you have a target or a key that you want to find in that array. Now I'm just telling you that, can you give me a predicate such that binary search is applicable on this search space? You can apply binary search on this search space. You will be able to apply binary search on this search space. Can you give me one such predicate, PX? Yes. Let's do an F star T star. Let's just make it a point to do F star T star always. Okay. So then Anurag, can you change your predicate accordingly? Yeah.
X greater than target.
Yeah. So let's, with this predicate X greater than target, can I say that binary search is applicable? Yeah. So for some elements, let's say the target is somewhere here. Before this element or up to this element, this predicate will evaluate to false. Correct? And after this, it will start evaluating to true. So with no problem, Sarvari. It's just that we are, so you can go ahead with either an F star T star predicate always or a T star F star. Both of them are equivalent. So I like F star T star. So I generally go ahead with this. So that's why we just. Sorry, what is the question? We are assuming target is greater than the smallest element in the array. Not necessary. Even if target is smaller, even if target is here, what will the search space evaluate to? All trues, right? Then also binary search is applicable. I told you, right? When there is only Fs, only Ts, then also binary search is applicable. It's fine. I told you the expression is F star T star, which is 0 or more F's followed by 0 or more T's. So this can be 0 or this also can be 0.
So does the efficiency also depends on the number of F's and the number of T's? Like if we have a program or a predicate with 5 F's and 3 T's, or like 6 F's, or the other way around. So like, does that the predicate comes related to efficiency in any case?
It can typically, but I will tell you that, I mean, in the second part, that with this, you can only find a certain, you can only find two types of elements, the last F and the first T. That's it. So this is all you can find with, so if you have a predicate wherein you have less F's and if you have a predicate wherein you have equal numbers of F's and T's, then roughly, yes, you would mostly find it in 1 or 2 steps, because you have to find this, which is roughly at the middle. That's the idea. We will discuss, and I think your question will be answered then. What is the question, Mrigank? No, it should not repeat. It's just F star T star. It's not F star T star, F star T star. No, what you are saying will not work. Yeah, I mean, you can take up any predicate. You can take up, yeah, like the predicate that Akshay says, let's say any dummy predicate wherein you say that is X less than 3 and greater than 5. Let's say just one range you are taking. 3 and greater than target. Let's say this is the predicate. Then basically only for some portion of the search space, it will be true. For others, it will be false. And this part also, it will be false, right? So then it will be F star, T star, F star. So then binary search will not be applicable.
Sir, what is the meaning of like efficiency of a predicate?
We will discuss. Don't worry. Yeah, let the theory proceed. I mean, theoretically, you can take anything as a predicate, Vaibhav. But the problem is with this, the point 2 will not be applicable. With that, you will not be able to solve the actual problem. So you have to design a predicate keeping that in mind as well, which is what I will discuss now. How is F star T star F star different from F star T star? F star T, both the regular expressions are different, right? F star T star F star, like I didn't get your question. This is F star T star in English means that series of 0 or more T's. That's it. After that, there is nothing else. This is series of 0 or more F's, nothing else. So it's not that 0 or more T's. After that, you cannot start anything. Like you cannot write any Tom, Dick and Harry after that. Any more questions? Let's move. Abhishek, what is the question? Just the last question. After that, we'll move. When a true or F occur, the condition PA implies PB doesn't come again. Can you unmute and ask the question?
Yeah, so in the T star, F star or F star T star arrangement, on the border where T and F like meet, so there's a T and then there is a F. Right. So P of A implies P of B doesn't hold there, right?
P of A implies P of B doesn't hold there. So you're saying, no, it will still hold, right? If I'm here, I'm making a comment about elements to the left. If I'm here, I'm making a comment about elements to the right. Right?
Yeah, okay.
Okay. So now once I have a predicate in mind, the next step is the theory says that if you have reduced your search space to a series of Fs followed by a series of Ts, then you can use binary search to find the last F or the first T. This is what the theory says. In log n time. Without any proof, I just state this. Okay. So this is the second part. I was telling you that even once you have the predicate, binary search framework will tell you what kinds of items you can search in the search space. So you can only search the last step or the first T in log n time. Okay. So now knowing this, let's say I give you the same question wherein I tell you that I have a sorted array and I have a target. You guys are more familiar with key. So I have a key that I have to search in this array. Can you apply binary search on this? That's the first question that I have to answer. And then the second question is, can you come up with a predicate such that you can apply binary search also and find that key also? I mean, my question is find this key in this array. How will we approach it? Just hear me out. How will we approach it? This is the idea that I was discussing on the right hand column. We will first, we know that it's an explicit search problem. It is given in the question that I need to search something in some search space. So I will first check whether I can find binary search, apply binary search on it or not. And if I can apply, then I need to devise a predicate such that my key comes as either the last F or the first T, right? Then only I will be able to search for the last F or the first T. Do you get this point? Correct? So that's it. So now you have to, both of these will actually go hand in hand. It's not like you will do an analysis independent of one another, but yes. So can you tell me of one such predicate? What if I do X greater than target or key? If I do X greater than key, then what can I find? If I do X greater than key, then I know that all these T's are obviously greater than the key, right? Because the predicate holds true for them. So I can look for the last F then in this search space. Once I get the last F, I can check. So the last F actually holds this property, right? X less than equals key. It does not necessarily hold this property, right? We want this. We don't want this. Correct? So I can find the last F and I can check for that last F, that if that last F is actually equal to my key, then I can return found or the index, depending on what the question is asking. Else I can return not found. Because if this F is not equal to key, then definitely nothing else. Everything else here is less than the key. Right? So this is what I meant when I said the third, when in the right hand column, I was talking about the third part, wherein I said that once you know that, you will have to judge for yourself whether finding the last F or the first T will help you in solving the actual problem. Here, finding the last F is helping me in solving the actual problem. I will still need to do an additional check after that, but yes, it does help me solve the problem, right? So this is how I will approach a typical question, a binary search question. Does this example make things clear? Do you understand why last F cannot be returned as it is? And you still need that check? So that's it. That's it. That's the theory of binary search, nothing else. I mean, we are done with the theory. If you understand this much. If there is any question, please feel free to ask me, because once we start solving questions, we will make use of this in every question, virtually every question. So now I know, so okay, so I just told you two things. I told you is binary search applicable or not? I told you with that you can find the last F or the first T. The third promise that I had made you was that I will give you the codes to find the last F or the first T. So let's write those two codes, and then we are done. Then you can just plug and play those codes and be happy. So now for finding the last F, I will write the code. How do we find the last F in a binary search using this framework? Okay. I am also thinking out aloud, so bear with me if I make mistakes. So low will store the starting of the search space, let's say, and high will store the end of the search space, something, let's say end. Okay. My while loop will basically run as long as low is less than high. I will do a mid computation, but let me think, how will I do that? Let's talk about the decision making. This is one thing that you will have to think through too. And then the third part is the sanity check, which we will come to. So now let's talk about the decision making. So I will basically evaluate the predicate at mid. This is what I will do. I will check if P of mid is true. If P of mid is true, then what happens? So now think, I have a series of Fs followed by a series of Ts, and my predicate at some mid index, let's say this was the mid index, evaluated to true. I have to find the last F, keep that in mind. So can I safely skip this element as well as everything to the right of it? Because I need to find an F. So I can skip everything including this element. So what can be my next bound? I can say my high is mid -1, right? Otherwise, if it is false, if predicate does not evaluate to true, that means I am somewhere here. I might be here, I might be here, or I might be somewhere. Let's say I'm here. So now, let's say this is the mid. So can I safely skip everything to the left of it? But I cannot skip this, because this might potentially be this element, because I want to find the last step. So my best or my safest bet is to keep this element still in the search space, but I can skip everything to the left of it. So I can say low is mid. Right? Is this decision making clear to everyone? Two, very simple. Which part, Sharvi, do you want me to repeat? The true or the false or both? So I evaluated the predicate at the mid. Yeah, I can, don't worry. So I just evaluated the predicate at the mid. So this is my search space. This is my search space, okay? I have evaluated my predicate and I know that my search space is of this pattern. FFF, TTTT. Now I have evaluated my predicate at the mid somewhere. Let's say this was the mid and it evaluated to true. Keep in mind that I am looking for the last F. Okay. So this was my low. This was my high. Now, if I'm looking for the last F, I can update my high to this index. If I'm here and if I encounter a true here. Why? Because I'm looking for an F. So I can skip every T including this T and every T to the right of it. which is what I have done when I wrote a high assign mid -1. This was mid and this is mid -1.
So
Similarly,
the mid can be the first T as well, right?
Doesn't matter, yeah. So what?
So
I am looking for the last F.
okay.
Yeah. Similarly, when I am at an F, let's say this is the mid, and I am here, I evaluated it to be false. So I cannot skip this F, but I can skip every F to the left of it. This F can be my potential F, right? But I definitely know that if there is an F at which I am standing, then any F to the left of it is not a candidate. That much I know. I cannot comment on this current F, whether this is the answer or not, but I can comment on everything to the left of it, which is how I will update my low to mid. So I will not update my low to mid +1. I cannot skip this because it can be the last F. So it's in my best interest to keep this in my search space. Is it clear now? Those two folks, Sarvari and Akshat. Yeah. So that's basically the decision making. I will come to how to find mid. Don't worry. Just follow along with me. Then we can't find anything in all trues or all falses. That's the scope of minor research. It tells you that I can only give you the last step for the first T in log n time. I cannot guarantee log n time for anything else. That's the scope basically.
So, no sir, when we choose a predicate which is giving all falses or all trues, then we can't find any key, right? We'll not be able to find, right?
Yeah, so we will return not found.
Okay.
I did not get your question completely, maybe.
So I'm asking if we are using a predicate which is giving series of all falses or trues, let's say. Then what? Like we are finding first false and last false and first true here, right? So in that series where we have only falses or only trues, then what can we find there?
What can we find there?
Yeah, because binary search is applicable for all falses or all trues as well, right? If a predicate is giving all falses or all trues.
Yeah, I mean, we can find this F, right? And we can...
Okay.
If it is all trues, then we can find... we can find this, we can find this, or we can find this, or we can find this, depending on how you are looking at it. Right? If you're looking at it as a T star F star, then if you're looking at this as F star T star, then this is basically the last step. And if you're looking at it as T star F star, then this is the first step. Right?
Okay, sir. Thanks.
Sir, what if mid is the first T itself? Then the if condition seems absurd.
What if mid is the first T itself? So, like, I did not get a question.
So then if the mid is first T itself, then in the if condition we have written high is equals to mid -1.
Yeah.
That is not making sense. Right?
Why?
If we have found that first T, then why we are subtracting 1 from mid?
We are looking for the last F, first of all, in this code, not the first T. First T is code I will write separately.
Okay, so yeah, got it, my mistake.
But even then you can like say that same argument for this else also. That if I am already at, if my mid is already the last F, that does not mean that, see, we want to guarantee log n time in searching for that last F or the first T. That's all we are guaranteeing. We are not saying that if the element is at the mid, I will give you in the first go itself. That kind of claim we cannot make because that's not generic. That's very specific to the input itself, right? We can only say that no matter what input you give, if I have this F star T star, I can give you the last F or the first T in log n time. That's it.
Okay, sir.
So you should evaluate an algorithm accordingly. That is this giving me the last F or the first T in log n time? You should not say that, okay, if I get the last F in the first go itself, why am I doing log n steps?
Yeah.
Yeah. So then the third part is basically doing the sanity check. So once I'm out of this while loop, I am left with one element, just one element. And that element, I will check if it is the last F or not. How will I check if it is a last F or not? I just need to check whether it is an F or not, right? So I will just check if predicate is false for that element. For P of low, is the predicate false? If it is, then I can return that element. Otherwise, I can return -1. So this is basically an all T sequence for which I was looking for the last step, which I did not get. This third part, do you get it? I am just doing a sanity check. Once I am out of the loop, I have a single element that I am left with. So I'm checking is it this F or not? If this is F, then I return it. If this is not, then I return -1, not found. So then basically there is no F in the space itself, in the search space. There are only T's. Correct? Can you act if you understand this? Then we will move to the more involved analysis of mid. Simple, but I can repeat if anyone does not follow this.
So what are we returning in the last step after we exit the if?
Return low, otherwise return -1. Low and high are the same, right? Once we exit the while loop, that is basically the last element that I am left with. So I'm just returning that. I'm evaluating the predicate on that last element, P of low. Correct, Akash? Do you get it? So think about it. Meanwhile, we will get to this calculation of mid. So mid, now, which one, Akash? Do you want me to repeat? If you have, finally, when you are diminishing your low and high, there will be a point when your low and high will point to the same element, right? That is when you will exit. When low equals high, you will exit. Because you are continuing as long as low is less than high. This return you're talking, right? There is no return statement in the while loop. These return statements are outside the while loop. Where is the return statement? Into. This is if P mid, high is mid -1, else low is mid. So just stare at the code. I guess you will get it. Otherwise, I will be happy to tell you again. Let's move on. We will talk about the mid now. So there are two types of mid in any array. You have, so this is your low, this is your high. Depending on, let's say you have a array of size 4, you can have either this as the mid or this as the mid, right? So this is called a lower mid and this is called a higher mid. So for finding the lower mid, the best way to find a lower mid is through low plus high minus low by 2. And finding a upper mid is low plus high minus low plus 1 by 2. Okay, so this is the lower mid and this is the upper mid. So in number 1, we have to decide whether we want to use a lower mid or an upper mid. That's the only decision that we have to make, and then our code is complete. So that decision, so first of all, do you understand lower mids and upper mids, or do I need to go in deep into that? Do you understand these two lines, as well as the fact that for even sized arrays, you can have lower mids and upper mids? So Sriram, basically you have an array of size 4, right? Any even sized array, you can have 2 mids, right? Just think about this. This is 0, 1, 2, 3. You can have either a lower mid or an upper mid. How? Because the mid is not really, so in case of an odd array or an array with odd number of elements, a mid is clearly defined, which is definite, you know, because you have even number of elements, n by 2 here and n by 2 here. So you know that mid is clearly defined and it's one element. But in case of an even sized array, you don't know which is the mid. You can have this also as the mid and this also as the mid, right? So this mid we call lower mid, and this mid we call upper mid. Okay, so for instance, if I have an array of size 6, then this is a lower mid and this is an upper mid. And I just gave you the mathematical way of finding out the index of the lower mid or the upper mid. Lower mid is low plus high minus low by 2. Upper mid is low plus high minus low plus 1 by 2. So basically you have a low, you have a high, low. So it's basically base plus offset, low plus this distance. So what is this distance? This distance is this entire distance, which is high minus low by 2. And for the upper, it is this entire distance plus 1 by 2. That will give you this. Okay, so this is low plus this, base plus offset. So now we have to decide whether we want to use a lower mid or an upper mid for this question, for this case. So I will just take it from me that you need to analyze only a case of size 2. So just analyze a case of size 2 of this type and determine whether you want to use an upper mid or a lower mid. How will you do the analysis? Just follow. Assume that you have an array of size 2 and let's say this is the search space F and T. So your low will be this, your high will be this. Okay. Now let's say you are using a lower mid. Okay. Let's say you go ahead with a lower mid. So your mid will be this, correct? So if your mid is this, just evaluate the algorithm. P of mid will be false. So it will come here, else your low becomes mid. So your low again remains as it is. So don't you have an infinite loop here? Did anyone get this? Yeah, I will take questions. So you cannot use a lower mid. So use an upper mid. Now for an upper mid, you can do an analysis. Similarly, let's say you go ahead with an upper mid. So this will be the mid. So P of mid will be true. Then high becomes mid minus 1. So your high comes here. So you are good. You are not getting into an infinite loop. So use an upper mid here. Just take it from me that you use for finding this, always use this FT and do this analysis, because this is the only problem. This is the only search space which can result to lead to infinite loops. Otherwise, you are fine with using either a lower or a upper mid. Okay. So people who understand this, can you write with pen and paper how to find the first T similar to this? It's very similar. There is no rocket science. Can you write the code to find the first T? And meanwhile, I can take questions from others who don't understand. Yeah. Tanya, you had a question? Yes. For an even-sized array, lower mid formula. Yes. Okay. So what is the lower mid? It is, the formula gives high minus low is 5 minus 0 by 2, which is 2. Yeah. Because these are all integers. So it's 5 minus 0 by 2, which is 2. And you take 0 plus 2, which is 2. And for a upper mid, you take 0 plus 5, 5 minus 0 plus 1. So 6 by 2, which is 3. 0 plus 3, which is 3. Karan, which part you don't understand? The analysis of the infinite loop? So I just told you, just take from me that your infinite loop will always come for this case, FT, a search space of size 2, wherein the search space is F and T. So just do this analysis for, or first take a lower mid and do the analysis, and then take an upper mid. So do the analysis. You have an F and a T, take a lower mid. If you take a lower mid, what is the mid? Mid is 0, right? Do you understand this, that mid is 0? So if mid is 0, then it is F, right? So if it comes to this else part, right? So low is mid. Your low was already mid. So your low still remains mid. So does your search space reduce now? No, right, Karan? Do you understand this? Your low was already here. Your mid was also here. Now you are updating your low to mid, but both of them are already at the same position, which is here at the F. So for the next iteration also, low is this only and high is this only. So you have an infinite loop, right? Again, you will do the same thing. Again, your search space remains FT. It's not diminishing or reducing by half. Do you get it, or are you just saying okay for the sake of saying? Okay. So now tell me, what will be the code for first T? Can someone unmute and speak up?
So if P mid, then high equal to mid, else low equal to mid.
Come again, 1 second. Let me clear this. So I want to find the first T. So you are saying while low less than high. I don't know the mid, let's see. But you're saying if P mid, what is the decision?
High equal to mid. High equal to mid.
High assign mid. Okay. Else?
Low assign mid.
Low assign mid. Mid plus 1, right? This is F. So you can skip that F.
So can you explain this low equal to mid plus 1? I'm getting the high.
Because this is else, right? So the else part is you have a false, right? So if you have a false, you are looking for a first T, you can skip this false also. It does not matter. So I can move my low to 1 plus the mid, just after the mid. Do you get it? See, this is F's, these are F's, and these are T's. If you are here, you are looking for this element. If you are here, you can skip everything to the left as well as this. So you can make your low here. Why do you want to keep your low here? Because you are looking for the first T.
Understood.
Okay, what is the sanity check then?
P high, then return high, else
P
return
high,
high.
return high. Yeah, Vaibhav, that is wrong. P mid will mid also be mid might not be equal to low or high, right? After you exit from the loop. Okay, and what about the mid? Will it be a lower mid or an upper mid?
Lower mid.
Lower mid. So how do you do the analysis? You have an FT. Okay, this is a low, this is a high. Let's say you go ahead with a lower mid. You have a mid here. So it is false. So you come here. You go to low is mid plus 1. So you go low is mid plus 1. So you are good. Right? So this is the code for the first T. Sanity check, sorry, is nothing but I'm just checking whether it is a T or not. Because once I have exited from the loop, I just have one element and I'm looking for a T here. So I just check, is it a T? If it is a T, return it, otherwise return not found. How do I check if it is a T? Obviously, it should evaluate, the predicate should evaluate to true at that last element. What is that last element? Either a low or a high. Both of them point to the same element, which is the last element.
The sanity only fail if all the F's are there, right?
Yeah, only fail only if you have all F's. So this brings to an end the theory. So I will take a moment to answer your questions and then we will start doing questions one after the other. No questions? Is it clear to everyone? Fuck. Everything is clear to everyone. Nice. Shruti, is it clear? Savio, is it clear? Sakshi, is it peace? Sarath, is the pace of this batch good for you or is DSP too good for you? Sushrit, is it clear? You were there in the last batch also, right? I don't know whether you were there for binary search or not, but pretty much it was the same. Radhika, is it clear? Puneet, Pranav, Manasi, Mrigank. Mrigank, why are you so silent today? Gaurav, is it clear? Ayanwa, Ashirwad, Aman, Anushka, Anurag, Akshat, Akash, is it clear? Abhishek, Ayush. Fuck, it's clear to everyone. I'll have a good sleep tonight then. Okay, let's do questions then. And so now is the time to brace yourselves because questions are coming. So questions are, you want to do a puzzle first? Does everyone want to do a puzzle? Is everyone mentally tired? पजल करना है, क्वेश्चन करना है, पजल करना है, चलिए पजल करते हैं। हाँ बस हो गया, थ्योरी इतना ही था, अब इससे ज़्यादा बकचोदी नहीं है थ्योरी में। अरे बहुत बहुत एब्स्ट्रैक्ट है थ्योरी, आई नो। ओके, पजल करते हैं। पजल मैथमेटिकल करना है या लेट्स डू अ मैथमेटिकल पजल। So the puzzle is somewhat sexist, but yeah, that's how it is. तो puzzle ये है कि you have a society or a village where people prefer boys over girls, and what so basically what happens is they keep having girls until they have a boy. Okay, so every family member keeps having girls until they have a boy, and once they have a boy they stop. So they might in the process be having 5 6 girls before they have a boy, or one girl then have a boy. हाँ मतलब ये विलेज है, मैंने नहीं बनाया विलेज। तो this is the situation in the village. So what you have to find is, you have to tell me the average number of girls per family. Do you get the question? Does everyone get the question? अरे मान लो कुछ C families, it's fine. C families, it does not matter. You can take some constant, it will cancel. N क्या है भाई? What is N? Average number of girls per family is N plus 1 by 2. No, that's not right. Okay, I will tell you the result, just prove it to me. Average number of girls per family will come out to be 1. Yeah, it's an EGP, Tanya, you're right. Yeah, it's an EGP. But it will come out to be 1. And that's why this puzzle is a popular puzzle, because it contradicts most of our intuitions. Like our intuition is that average number of girls per family should be at least more than 1, right? Average number of boys per family is 1, right? Because every family has exactly 1 boy, right? So average number of boys per family is 1. But average number of girls per family इससे तो ज़्यादा ही होना चाहिए. That's the intuition that we get. But no, it is 1. Yes, we assume girls and boys are equally probable. So just prove it that it's 1 mathematically. खाली लिखना है, इसमें और कुछ नहीं है. मतलब लिखते रहोगे तो हो जाएगा at some point. Just do an expectation calculation, nothing. What is the expected number of girls per family? Yeah. Did you get it? It's an infinite AGP. So just do the math. It's basically what is the, just see Karan and then we can discuss. So what is the expected number of girls per family? That's what you have to find, right? So what are the cases? You can have a boy straight away, right? You can have a girl boy. You can have a girl boy, girl boy, girl boy, and so on. So what is the expected number? Expectation is xpx, right? So x times probability that, so x is 0 here, 0 number of girls. Probability of this sequence is half, right? What is for this? There is one girl. What is the probability of this sequence? 1 by 2 into 1 by 2. For this, two girls, probability of this sequence is 1 by 2 into 1 by 2 into 1 by 2. Three girls, probability of this sequence is 1 by 2 into 1 by 2 into 1 by 2. Four girls, 1 by 2 into 1 by 2 into 1 by 2. So this is the sum. So you can say S is, so this is an AGP if you see. And so on. So how do you solve this AGP? S by 2 say you can subtract, right? How have you been taught to solve AGPs? यार हम लोग को कोटा में तो ये सिखाया गया. This is how we've been taught. Subtract by S by 2. So this is, you have another half here, right? So basically you subtract by S into R. R is the common ratio. So now what happens as a consequence is, see this, these two are subtracted. So it becomes 1. These two are subtracted, it becomes 1. These two are subtracted, it becomes 1. So basically now you can do this. This becomes S by 2. This is 1 into half plus half into half, 1 by 2 to the power 3 plus 1 by 2 to the power 4 and so on. Right? So this can be, if you do this, A upon 1 minus R, which implies S by 2 is half, S is 1. Okay, सही है ना ये? Do you get this? Yeah. So this is basically cool. Shall we move on? How will you do direct expectation, sorry? Okay. So now let's get to the real deal and address the elephant in the room, which is binary search questions. Let's start with okay, let's start with peak index. Let's try this question. we will use the predicate framework for all these questions. Shall we discuss? Let's discuss this question. So the question is telling you that you have a mountain array. What does that mean? That means that you have an array. So just follow along. I will show you a couple of questions and how we can use the predicate framework for them. And then after that, you can, I will give you some questions that you can try on your own. Okay. So here you have been given a mountain array, which is basically an array of this pattern, an array which looks like this in picture, and you have to find the peak index. Okay. So let's think about how we can do it using the predicate framework. So this is the search space. Okay. The first thing is, can I apply binary search? And if I can I come up with a predicate such that I can reduce this search space to F star T star? That's one thing. And the other thing is my last F or the first T should be this peak. Correct? I need to design a predicate keeping both the things in mind. Right? Does everyone understand this? So what kind of predicate can give me this? Just think. So if you see, just before the peak, the slope is increasing, right? And just after the peak, the slope is decreasing. So can I use that as the predicate somehow? How do I quantify slope?
Delta y by delta x.
Yeah, I mean, I can do array I minus 1. Right? Can I say for this half, every element is greater than its left element. And for this half, every element is less than its left element. That's the property, right? So can I use that to frame a predicate such that it is F star T star as well as the last F or the first T should give me this peak? Are you guys getting the line of thinking? So tell me, what could be the predicate for this?
So we can do A2 minus A1 should be less than 0.
A of I can simply say A of I is less than A of I minus 1, right?
Yes, sir.
This for this predicate will be true for this half, right? Yeah, exactly what you guys are also saying. I plus 1 also you can do it fine. So it will be true for this half. For this half, it will be false, right? So now just how will my search space look like for this predicate? It will be false here, false for everything. For the peak, will it be true or false? It will be false, right? And then it will start becoming true from here, because from here it will start, right? So now I can use this predicate. Now tell me, if I have to use this predicate what do I have to find? The last f or the first t? The last f, right? Because the last f is, so I have to find the last f. So good, now go. And so just plug in that code. That's the answer. Plug in the code of last f. Okay, that's the answer. Just see me coding this. So the screen is visible, right? Our first code for today. I know that I have reduced my search space to a series of f's followed by a series of t's. My predicate is nothing but ai is ai less than ai minus 1. And I know that I have to find the last f. Correct? So far, this is what I have, my analysis that I have done. So now let me just get the size. I need the low, the mid, and the high. So I will initialize my low and mid. Low and high. Low is 0, right? And high is n minus 1. So now I'm just writing the code to find the last step. But because I have not memorized it, I am taking also while I'm writing. So while low less than high, I will think about the mid. I don't know. Let's see the decision first. So my decision is if P of mid. So what is P? P is this. So if P of mid. So if A of mid is less than A of mid minus 1, then it's true. So if it is a true, I can safely skip this. So I can do a high is mid minus 1. Otherwise, if it is a false, then I cannot skip this. I can do a low is mid. How do I calculate the mid? Do the analysis. It will come to, so generally I can just give you a trick for calculating the mid. It is generally that mid for which you are not taking the mid in the search space. So for this statement, you are not taking the mid element in the search space, right? Further. So your mid will be this mid, which is high. That's one way of remembering it. Otherwise, you can go ahead and do the analysis. This is it. Now in the sanity check, do I need any sanity check? I don't need any sanity check because it's given that there is definitely an index. So I know that whatever element I'm left with is always the peak. So I can simply return that. Do I have to return the index or I have to return the index, right? Let me just refresh. Okay. Any questions? Are you following what I'm doing? Is everyone with me so far? Do you see now are you getting an appreciation for the framework and how we are applying it to questions? Yeah, otherwise like you can keep scratching your head over how I directly write mid. That's a good question. So for everyone, just see. That's basically you can, yeah, I will just tell that. The trick is nothing, but you can just look at that line where you are not considering mid. So in this, while you are not considering mid here, right? Out of these two lines, either this line or this line, which line you are not considering mid? You're not considering mid here. Okay. So if you are not, so then use this mid, which is high mid. So I use a high mid. Did you get it? Yeah. Because that's basically, I mean, intuitively also, that's basically the line which is helping you progress in the case of two elements. This line is not helping you progress. Okay, let's do more questions. Let's do a slightly more difficult question, but again, not very difficult. Let's do this and things will become clear. This will help clarify a lot of doubts. Any ideas how to do this? These are not easy questions, I understand, but with practice, you will be able to master some of them, at least.
Do we have to just find the last f and first true with the predicate AI greater than target?
No, that's not all. That's not complete. I mean, that's wrong also in some ways. You have to do a last step in a first T, but it's slightly more involved than that. Yes, you have to use two predicates. We will see. You have to find last f and first T. There is no doubt about that, but you have to use two predicates. You cannot just do a greater than predicate and that won't be enough. Yes, two different predicates, yes. The whole process you'll have to do it twice, yes. So let's see. Let's find the first occurrence first. So question is basically you are given an array of numbers and you have to find the first occurrence of an element. So you have an array of numbers. So let's say this is the half which contains the same number. Let's say 3, 3, 3, 3, 3, and you want to find the first index and the last index of occurrence of 3. That's the question. So now let's think about it. You have an array. Let's say this is where 3's start. Let's say this is where 3's end. It's all 3's here. After this, you have greater than 3. After this, before this, you have less than 3. Okay, because the array is sorted, it's given. To find the first occurrence, you have to find this index, right? Which means that either your last f needs to be this, or your first t needs to be this, right? If you have to find this index has to be either your last f or the first t. That's it. So how can you make this index, the index just before the first or the index where 3 occurs, as the last f or the first t? Let's think. Can we make it the last f? Can anyone? We cannot make this the last f, because if this is f, then everything to the right of this, these also will be f, right? Because the predicate will evaluate to the same value for all the elements. So you definitely cannot make the first 3 as an f such that this is the last f. Do you follow this? Because other numbers to the right of 3, which are also 3, predicate will evaluate to the same value, right? So they will also evaluate to f. So this can never be a last f. So the only possibility is you can make this the first t. That makes sense. If you make this the first t, then yes, these can also be your t's. And so now give me a predicate to make this the first t. That's straightforward, right? What, L plus 1? No, you have a target which is given. Yeah. AI greater equals target. In this case, the target is 3. Right? So use this predicate and find the first t. That will give you the first occurrence. Similarly, you can just think through. Now I want this answer from someone. Tell me, do a similar analysis for the last occurrence. It's not very hard now. At least now it's not very hard. So again, I will draw the picture for you. This is an array. This half you have all 3. You want this index. So my question is, you have first t. Can this be your first t, or can this be your last f? Can this be your first t? Can someone unmute and speak? Yeah, I mean, you cannot make this the first t, because if this is your t, then these also will be your t. So this cannot be the first t. This will be the last f definitely. And if this is the last f, then what is your predicate? Your predicate is AI strictly greater than the target. So बस now code कर लो आप लोग. Same यही predicate use करना है. Now you know the template for last f. Use this predicate and code 2 बार कर दो. बस that's the code. Okay. So I will code it. Just see how am I coding it. Will make things clear to. So first I am trying to find the first occurrence. How do I find the first occurrence? I know that I want to use f star t star. I also know that my first occurrence will be the first t, but let me first write the predicate. So my predicate is num psi greater equals the target. And I have to find the first t. Let's do this. You have a low, you have a mid, and you have a high. Initialize your low to 0, high to n minus 1. Let's start the loop. I will see how to write the mid. I don't know right now, but let's do the decision making first. If predicate, I will evaluate the predicate on the mid. So my predicate is this. If it is true, I have to find the first true, so I cannot skip this, but I can definitely move. If it is true, then I can definitely skip everything to the right of it, right? So I can write I is mid. If it is false, then I can skip everything, including this. So low is mid plus 1. So what will be the mid? Mid will be dictated by this line, because this line, it does not include the one, does not include mid. So what is that? Low. So your mid will be low. What is the sanity check? Sanity check is this the number, right? That's the sanity check that you have to do here. You just have one element left, which is basically greater equals the target. You have to check now whether it is equals to the target. So just do that. If it is not equals to the target, which means that it will be greater. Let's make it more. If it is greater than the target, then you know that the number is not there. So you can just return from here itself without going into the second pass, right? Otherwise, it needs a vector as the result. So I can just push back this number. Does it need indices, or it needs indexes, obviously. Yeah, so this first occurrence is clear to everyone. Can you hack? People who have problems with syntaxes of C, for them also, is it clear? The pushback and the returns, all clear, right? Okay. So then just go for the last occurrence similarly. So last occurrence, you want restart. Your PI is basically nothing but if you want the last occurrence, you want it to be strictly greater than the target, and you want the last occurrence. So I don't know how to write my mid, but I will come back to it in some time. I will check if predicate is true, then I can skip this. Otherwise, if it is true, then I can skip this, right? Otherwise, I cannot skip it. So my mid will be governed by this line, so it's a high mid. What will be the sanity check? There is no sanity check actually needed, because since the first occurrence was there, you will obviously always find the last occurrence also. It can be the same as the first occurrence, that does not matter, but you will always get it. So you can do this. There is no sanity check needed here. And then you can submit. We are all going to refresh. Yeah, it's just for an empty. You can take care of that here. Just here. It is trivial, I mean. What is the issue? Can anyone tell me what is the issue? The issue is this. This will be not equals. It can be less also. So this is the code. Do you understand why this is not equals and not necessarily greater than?
No, sir.
Have you guys slept off? Are you still alive? Yeah. So whatever is left, just think about the last element. The last element that I have is a true, right? So what is the criteria for a true? The criteria for a true is that that number is greater equals target. That much I know. If it is true, it can, so the last number can be true or can be false, right? If it is false, then definitely I have to return -1 -1. So if nums low is less than target, then I have to return -1 -1, right? If it is true, then also there is a case when I have to return -1 -1. When it is strictly greater than the target. So those two cases I have just encompassed here. The other way of writing this could be that you can do this. Otherwise, you can return this. This is also good. Do you follow? Should I explain it on the board? I can explain it on the board. It's fine. Just let me know.
Can you explain how did you combine the two conditions earlier? This one's fine, but combining, how did you actually combine?
Nothing. Greater and less. So greater than, less than, I just said not equals.
Okay.
Right? For both greater than target and for less than target, I have to return -1 -1. So I said, if it is not equals to the target, return -1 -1.
Got it, sir. Got it.
So these cool. So the whole idea behind explaining these is not for you to just understand. You should be able to create these solutions on your own. That's the goal. And that's basically the level of practice you have to do. You have to reach that stage where you can write this code on your own. Of course, if somebody gives it to you, you will be able to understand. All of us will be able to understand. That should be I mean, that will not get you a job or whatever you want to achieve out of algorithms data structures. You should be able to create this on your own, this entire thing. So that kind of analysis you should develop. That will come with practice. There is no other substitute to that. I can give you the theory, I can give you examples to explain the theory, but yes, you will have to eventually like do the hard work of practicing. Okay, is it becoming too heavy for today, or shall we do more?
More.
Others, or do you have enough food in your plates already? Yeah, let's do one. Yeah, let's do this. So what is this question telling you? This question is basically
so the predicate can be AI greater than A0.
AI greater or less?
So greater than.
So this will be same as the mountain array problem.
If you're doing greater than A0, then it is true T star F star, right, Suraj?
Sir, it's less than, yeah. It's less.
Yeah, I mean, it's fine. I'm not saying that's wrong, but yeah, one of them. At one point, there will be a break in the increase and there will be a sudden drop. Yes, that's right. You are very close, Mrigank. So I will just explain to you what a rotated array is. So you have an array, it's sorted. So let's say 1, 2, 5, 8, 9, 10. Let's say you have this. I can post it, don't worry, Sally. So you have this array. Now what you do is you pick up a pivot. Let's say this is the pivot. What you do is you rotate this array. What does this mean? Just visualize it. Visualize this rotation about this pivot. So what you do is this part, you take it in the plane of the board and you come out here out of the plane of the board. So then so in other words, what you do is this entire part you just copy here as it is. After rotation, this becomes 8, 9, 10, 1, 2, 5. Right? So does everyone understand rotation? And I don't like to see this picture for rotated sorted arrays. I like to see this picture, which is basically it, as Mrigank was saying, it increases, then there is a drop, and this is how it proceeds. Right? And you have to find this number. So now think. Two things. I need F's for this part. Okay, I need F for this, I need F for this, I need F for this, so on till here. I need trues for this part and either F or true for this number, depending on my predicate. Can I do that? If you see, this entire line is below this line. It's below A0, and this entire line is above A0. Can I use that? Not really mountain peak. Mountain peak is, here it's increasing both the parts of the curve are increasing, right, Drishan? So you cannot use the slope wala logic here. Am I correct? Yeah. So what will be the predicate? Can I do a predicate AI less than A0? So this entire half will be strictly less than 0. And this entire half will be greater equals A0. Correct? So this will be F and T. So I have to find the first T. Correct? So this is basically the question. Now, Sushrit, you cannot use AI less than AI minus 1. This is again, slope is, how will you use slope as a demarcator for distinguishing this part of the curve from this part? You cannot, because both the parts are increasing. Right, Sushrit? Do I make sense? Yeah. So this is basically the predicate. AI less than A0 and you have to find the first T. Shall we code it? Let's code it. So I have F star T star. My predicate is num psi less than num0. I have to find the first. That's my question. So let's get to the actual real act of doing this. Low, high, low 0, high is n-1, while low is less than high. I don't know how to calculate mid. I will come to that, but let's do the decision making first. So nums of my predicate is nums of mid less than nums of 0. So if it is true, then I know that it is true, then I know that I cannot exclude this, but I can exclude everything to the right of it. Otherwise, I know that I can exclude this as well as everything to the right of it. Now my mid will be typically dictated by this line, so my mid will be a low mid. Now, once I come out, what is the situation? So I need to check whether it is a true or not. So if it is a true, then nums of low is less than nums of 0. So it is basically true. Then I can simply return, do I have to return the index or the number? The number. So I can return the low. What will I return if it is not a true? It's all falses then. Right? So everything is less than A0. Or everything is greater equals A0. I will return nums of 0 in this case. Just think why. Do I have to find the first t? What is the mistake? Can you tell me what is the mistake here? Index return नहीं करना. अच्छा, minimum return करना है. ठीक है, ये है कोड बेसिकली. Now you can ask me questions. High and low are the same, Vaibhav, once we are out of the loop. Right? We just are left with one element after we are out of the loop. So high and low are the same. So you can replace this with high. It really doesn't matter. You can do this. It's the same. Or you can do a low here and a high there. Or high, high. Does not matter. Okay. Are you guys getting this solution as well? Yes. ठीक है. After rotation, num0 is the pivot element. So how are we comparing with it? No, I did not get your question, Rekha. We are not comparing. No, we are comparing with the num0, which is after rotation. So we are comparing with this. With this, we are not comparing with this. Everything in this part is obviously greater or equals this, right? And everything on this in this part is less than this. ये फोटो आप देखो समझ आ जाएगा. ठीक है? Is everyone cool? Do you get binary search, albeit a little abstract, but yeah, do you get an appreciation? Does it make your life easier, this framework, or is it a burden? You can do whole lot of like spectrum of questions using this, and you don't really, otherwise, like if you're just doing without any framework, you can keep banging your head over corner cases and what you have missed, I plus 1, I minus 1, I by 2, made by 2. You can keep banging your head. This framework nicely captures all the ideas and gives you a nice proper algorithm to code. I will give you 2 questions that you can do at your leisure. We can discuss it. These are nothing but just modifications of the problems that we have done. So try these at your leisure. Tomorrow we will start with non-explicit search spaces in binary search. So binary search is basically used for solving two types of problems. One is what we considered today, wherein we had explicit search requirements in the question, and we simply applied binary search to search. Tomorrow, we will look at a class of problems which are optimization problems, which can be solved using binary search. So tomorrow's lecture will be like difficulty wise, it will be a little more difficult than this, but make sure that you study this. I will give you a reading assignment, a reading reference. In fact, I can paste it here also, but you will be able to find it in Slack also. Yeah, everything will go on Slack, don't worry. So this is a nice tutorial on the predicate framework of binary search, a top coder tutorial. So people who love reading and for whom reading is the way out to understanding things, you can read this. This will not give you a lot of intuition, but mathematically it will solve all your doubts if you have any mathematical or formal questions. So read this, practice these questions, make sure you have these things on your tips when you come tomorrow. Otherwise कल का lecture तो मतलब 2-3 floor ऊपर से उड़ जाएगा आपके. Tomorrow will be a little difficult, not very difficult, but yes, those are basically division 2 code forces C or D questions we will be taking up. Not very difficult, but yes, moderately difficult. All important for interviews. Okay? Is there anything else for me? Any questions?